Hi, today we will continue with chapter 5, part 2 on three-phase system. Okay, as we can see, this is the Y connection. So usually the three-phase system are divided into two. So the first one is called Y connection, and the second one is called delta connection. How we can differentiate? So we can see the connection will be in a Y shape. So like this, so it's Y, and delta will be different, so it will be in a triangle shape. So later I will show you on the delta connection. So for Y connection, so it will be like this. So usually the three-phase system will be three single phase circuit. So this is for first one, second one, and third one. So what we will do, we will connect these three return conductors to become one single return conductors like this. So from here, using this Y connection, we are creating a combination, a single return conductor. Okay, so you can see here, it has A, this is a neutral, B, and C. So initially it has six wires, six conductors. One, two, three, four, five, six. When you combine it like this, it reduce the number of transmission line from six to four. So you need four. So the return conductor is called neutral conductor and carries current IA plus IB plus IC. So it's in the middle. So it's a neutral conductor. Okay, so the sum of the three return current is zero at any instant. So this is the current, the graph for the current. So we have three. All these current are out of phase by under 20 because it's three phase. Okay, so why it says the sum of return current is zero? Because let's say you take at 240 degrees. So it's here. So IC is maximum. Okay, IC is I max. So IB, so here and this. So here it is the same. So this is actually so negative 0.5 I max. So this is I max. So this is negative 0.5 I max. So we can see I max minus 0.5 I max minus 0.5 I max. So you will get the value to be 0. So no current flow in the middle actually because it cancel each other and the neutral line could be removed. So initially we saw it has four lines. So we can remove this neutral line because it's not carrying any current. But the condition is the load must be the same values. Okay, so earlier from six line transmission line we reduce it into four. And now after we remove this neutral line, so we can further reduce it from four to three. So we call it as three phase three wire system. So actually, then some part of the three phase, we can see the neutral lines are there, and mostly now we can see is only having three phase three wire system to reduce the complexity. So this is the differences. So this is three phase four wire system. Four wire system has an additional neutral conductor in between, and three phase three wire system you don't have any neutral. So the neutral is only at the middle. Okay, so voltage relationship in Y connection. Okay, we can see the voltage relation between line and neutral. Okay, like here, this is line and neutral, and there's another term called line to line voltage. So I will explain to you what is the difference, and by understanding this, we can express in the mathematical expression, and we can do calculations. So generator winding voltage phasor diagram. So this is voltage phasor diagram. Uh, in this, this is the physical in the circuit. So the Y connection will be like this, and this is the phasor diagram. So you can see the induced voltage in the generator windings are EAN, EBN, and ECN. So these are the voltages generated by the generator. Okay, or we call it as line to neutral. So line to neutral, line to neutral, line to neutral. So this is the first type of voltage, line to neutral. Okay, and there's another value called line to line voltage. So line to line voltage is EAB. That is, so no n in between. Okay, so we call it as line because we have three lines A, B, C. So line to line means A, B, B, C, A, C, or C, A. Okay, that is what we call as line to line. So we need to understand the differences between uh, these two, line to neutral voltage and line to line voltage. Okay, so you can see if you want to find EAB, this is actually the combination of EAN plus ENB. Okay, so you plus these two together, you can get EAB. So this is vector in mathematics. Okay, so it's actually the same as EAN minus EBN because this is a vector component. So when you it's supposed to be NB, but if you change to BN, so you need to minus it. So you can use this to find EAB. Okay, then same for the other line to line voltage also, EBC, EBC, and ECA. Okay, so this is called the line to line voltage. Okay, so if I ask you what's the difference between line to line voltage and what is the difference between line to neutral voltage, you must be able to explain. Okay, and all these three are divided in by 120 degrees. Okay, EAB, okay, you can see here. So this is an example. EAB here is actually the combination. You see the arrow. This is a vector. The arrow is like this. So if you want to get this arrow, so you need to find plus EAN plus ENB. But since the direction is reverse, so this is actually a negative EBN. Okay. So similar like how I explained earlier. And if you want to find, so ELL means E line to line. So length of ELL of the phasor EAB. Okay, so this is the formula 2 times ELN times cos 30. So this is from the previous part 1. So you can refer to part 1 notes for this formula. So when you solve this, you will get ELL is actually equals to square root of 3 ELN. So you can use this formula for your calculation. So it means that line to line voltage ELL is square root 3 times more than ELN, line to neutral voltage. Okay, so you can see here the line to neutral voltage, so neutral is here, so E1, E21, so it's under voltage. Okay, here to here, under voltage. And so this is for E1, EB2, and EC3. Okay, all same. Under. Okay, that is line to neutral. So from here to the middle. You want to find ELL, or line to line voltage. So that is actually, so what's the formula? Square root of 3 times E 100. Okay, 100. So you get 173. So this is line to line. A to B is 173. B to C is 173, and C to E is 173. Okay, so this is for you to understand. Okay, so an example. So a three-phase Y-connected generator induces 2,400 voltage in each of each winding. So determine the ELL, line to line voltage. Okay, so sometimes it's written EL, sometimes it's written ELL. So I prefer to use ELL. Okay, so ELL equals to 2,400 times square root of 3 equals to 4157. So this is the line to line voltage. Okay, so another example. Okay, a three-phase 60 Hz generator connected in Y generates a line voltage or line to line voltage of 239,000 voltage. So determine on these components. So you can see the solution. So ELL equals to square root of 3 ELN. So this is our standard formula. So ELN is actually, if you are ELL divided by square root of 3. So ELL is 2, 3. We have additional 1 0 here. Okay, just reduce 1 0 here. Okay, so 23900 and divide by square root of 3, so you get 13,800 volt. Okay, the second part, the line induced in the individual winding. Okay, the voltage induced in the individual winding is line to neutral voltage, which is 13,800. So calculated here. So the time interval between the positive peak voltage of phase A and positive peak of phase B. So you need to find the time intervals. So one cycle, so 360 degrees, correspond to 1 over 60, because it's given here is 60 Hertz. 60 Hertz means so in 1 second you have 60 cycles. Okay, so it is actually equals to 1 over 60 seconds. Consequently, 120 degrees correspond to an interval of t. So we know, and for and the question asks for peak voltage of phase A and the peak voltage of phase B. So it's separated by 120 degrees. So 120 degrees correspond to an interval of t. So t equals to 120 divided by 360 times the time in second. One time 1 over 60. So when you solve this, you get 5.55 millisecond. Here the peak value of the line voltage Em equals to to find the peak value, Em equals to square root of 3 times 23,900. So you get that 33,800 as a peak voltage. Okay, so another example. The voltage between A, B, C of the below figure is 620. Can determine the voltage across each resistor, the current in each line if R equals to 50 and the power supply to the three-phase load. Okay, so ELN equals to 620 divided by square root of 3. So 620 is the effective voltage. So 620 divided by the square root of 3. So equals to 358 voltage. Current of each line. So this is already for each line. So 35. So V equals to IR. So V is 358. So 358 divided by 15 is R, resistance. So I is 23.87 ampere. And the power supplied to the three-phase load. Okay, so P equals to, so you need to find for three-phase load, not single phase. So you need to times with 3. So P equals to VI. So VI is the voltage induced E. So 3 times EI. So 3 times E is 3. E is 358. Sorry, 358 here. So there's some mistake. So times with 23.87. So you get 25.8 kilowatt. Okay, so that is some calculation for Y connection. So we go to the second type of three-phase, which we call it as a delta connection. So delta connection is the symbol of delta, okay, like a triangle. Earlier we saw the Y connection in the shape of Y. Okay, so this will be connected to the generator. So the line voltage are produced by the generator. Okay, the resistor currents I1, I2 and I3 are in phase with line voltage EAB, EBC and EAC. Okay, so all are in line with the respective voltages, and we can find IA, IB and IC using the Kirchhoff law. So all these are already derived. As we can see, IA leads I1. Okay, so this comes first, then I1 by 30 degrees. So the line current IL and the branch current IZ. So in delta we have two things, IL and also IZ. Okay. So IL is the line current, IZ is the branch current. Okay, so IL equals to 2 times IZ times cos 30. So this is similar like the previous formula. So you can get 2 times IZ times square root of 3 over 2. Okay, so once you solve this, so we know that IL equals to square root of 3 IZ. Okay, IL, the line current, is 3 times greater than the current in each branch for delta connection. Okay, so initially we saw so you can see EL. Okay, EL is square root of 3 times line to neutral voltage. Here we see IL is square root of 3 times greater than the current of each branch. So we don't have a neutral, but we have a branch. Okay, so we have a branch here. Okay, so almost the same line by connection. Okay, so three identical impedances are connected in delta across a three-phase 550 volt line as shown in the figure below. If the line current is 10 ampere, okay, line current is given 10. So we need to determine the current in each impedance. So we have three impedance. So we need to find for one in each. So the value of the impedance also we need to find. How to find the current in each branch Iz equals to so 10 is the line current. So divide by square root of 3 because line current equals to square root of 3 times Iz. So you rearrange the formula so you can get this, and Iz equals to 5.77 ampere. The second question is the value of each impedance. So the value of each impedance in each branch. So the voltage across impedance is 550. So Z equals to E over Iz. So this is formula V equals to IR. So E is 550 divided by 5.77. So you can get Z, the value is 95. Okay, so the summary of three-phase system. So this is Y connection. Okay, Y connection is like this. It is in the Y form. And this is delta connection. Okay, so a bit different in terms of estimation. Okay, here E is divided by 1.73, but here the current is divided by 1.73. Okay, so a bit like different. Okay, so you can see the division. So current in each element here is equals to line current I, but here it must be line current divided by square root of 3. So there are some differences so which you can go through. Okay, so it will help you to understand how to use the calculation. Okay, so I go to the next subtopic, the power transmitted by a three-phase line. Okay, so we see for Y connection first because we need to understand how the power is transmitted from the generator. Okay, so the apparent power S for each branch. to E over square root of 3 times I. So this is the formula. So the apparent power supplied to all branch. So since we have 3 branch, we times with 3. So you have square root of 3 EI, and these are the components of the formula. So square root of 3 is equals to 1.73. And for delta connection, as said, the apparent power equals to E times I over square root of 3, and the apparent power supplied to all branches. So you get this. Here we see an example. So three resistors are connected in delta. If the line voltage is 13.2 kilowatt and the line current is 1202 ampere, so determine the current in each resistor. So all this thing we will see accordingly. So first you want to find the current in each resistor. So I add so E square over square root of 3. So line okay, is supposed to be under 20. So under 20 square over square root of 3. So we get 694. So the voltage across each resistor is ER, which is 13.2 kilowatt. So the power supplied to each resistor is 13.2 kilowatt times with 694. We want to find the power supplied to each resistor. So the times the voltage times with resistor the current VI. So you get 9.16 megawatt. So the power supplied to the three-phase load, you need to times with 3. So you get 27.5 megawatt. In the resistance of each resistor R equals to 13200 13.2 kilo. So divide by your I 694. So R is 19 ohm. Okay, so another example. Phase motor connected to a 600 volt line, ultrasonic line current of 25 ampere. Calculate the apparent power supplied to the motor. So that is equals to EI. So in the previous formula, EI times with square root of 3. So 600 times 25 ampere times square root of 3. So you get 26 kilowatt ampere, kilovolt ampere. Okay, so there are 3 powers usually we will calculate in 3 phase. The first one is active power. So active power is P. So usually P equals to VI. So we can calculate this active power. Then we can calculate the reactive power S. Sorry, Q. So this is voltage times current times resistance VAR. Okay. And the current power S is voltage ampere, so voltage times current. But this is the formula. So square root of P square plus Q square. Okay, and cos theta is the power factor of three-phase load. So usually for three-phase, power factor must be determined. Okay, to understand uh, how the power can be distributed, and the angle theta is the phase angle between line current and the line neutral voltage. Okay, so usually the phase sequence, okay, there are a term called phase sequence. So the phase sequence analogy, so we can see whether it's counterclockwise or clockwise, because when the turbine is rotating the magnet in between, so we can see, so let's say A, E, C are divided into 120 degrees. Uh, so like in this figure, so we can see the distant counterclockwise like this, and your eye is here. So how we will see the sequence. So the letter appear first A, then when we move, B will come here. So we will see B, then we will see C. So the sequence will be A B A B C A B C. Even though these rotate counterclockwise, you will see in clockwise A B C A B C. So user defines here, this is considered as a positive sequence. So we can call it sequence ABC, BCA, or CAB. Okay, so this is the phase sequence. So when we use in calculation, we need to understand how to write it. So we are not writing it based on the direction of the rotating disc. We write based on what we observe first. Okay, so that is for when these turn counterclockwise. So when the disc turn clockwise, okay, same setup, but now the disc is rotating clockwise. So your eye is here. So when we rotate clockwise, so you will see A first, then you will see C, and you will see B, and it goes. So we always define this as a negative sequence, because you are, when you are observing uh, it in a counterclockwise sequence, A C B A C B. So we call it as a negative sequence. So the sequence will be A C B C B A or B A C. Okay, like this. Okay, so with that, we just conclude this chapter, chapter 5 on three-phase system, which covers two parts, part 1 and part 2. So thank you.